Hello, everyone, and welcome to another episode of Eyes on Earth, a podcast produced at the USGS Aero Center. Our podcast focuses on our ever-changing planet and on the people here at Aeros and across the globe who use remote sensing to monitor and study the health of Earth. My name is Tom Adamson.
Landsat has collected millions of images for over 50 years, documenting changes all over the world. Rising temperatures on polar ice are causing rapid changes, and Landsat has imaged lots of those changes. However, it's dark in polar regions during their respective winters, so a new project is adding more imagery of these dark polar regions so these changes can be studied in more detail, even in polar twilight. The project is called the Landsat Extended Acquisition of the Poles, or LEAP, and we're just calling it LEAP. Here to talk to us about LEAP is Chris Crawford, USGS research physical scientist, and within the Landsat mission, he is the Landsat project scientist and oversees the Landsat Earth data acquisition strategy. So Chris, let's first start with this. Why is it important to map polar regions?
Thanks, Tom. So polar regions on Earth have a significant percentage of perennial ice in the form of ice sheets, ice caps, outlet glaciers that flow into the ocean. The ice sheets have ice shelves that stabilize land ice, sea ice that forms seasonally around the ocean and around the ice sheets, and then snow cover on top of the ice. And so ice and snow are highly reflective to incoming solar irradiance, and thus very important for Earth's radiation balance to transport cold air towards the mid-latitude and equatorial latitudes through atmospheric and oceanic circulation. Mapping ice is critical for understanding variability and change in sea level. When ice mass goes up, sea level goes down, and vice versa. And so in terms of climatic changes on Earth, because the polar regions are changing much faster, and with the current trajectory of warming, mapping polar regions from remote sensing is a preferred observational technique because these Earth regions are remote and expansive.
And what can Landsat show us in these regions?
Landsat optically observes Earth's surface through measurement of reflectivity and temperature in polar ice and oceans, as well as across the Earth. And these are two key geophysical parameters for measuring and modeling surface energy balance. Landsat can observe both the spatial extent and the temporal variability in snow and ice cover and the coastal ocean ice interface. Because Landsat has 30 to 100 meter spatial resolution, Landsat can observe specific ice features such as calving glacier fronts and icebergs, surface roughness across the ice sheet, as well as cracks and crevasses indicative of ice movement and flow. Because Landsat can measure the emitted thermal radiation, it's possible to retrieve surface temperatures across the ice sheet and identify actually some of the coldest places on Earth. Landsat's spatial resolution can also help to resolve these warm pools that are a few degrees above freezing, where water is upwelling from the deep ocean, and these are called polynyas, and these features are seen within the floating sea ice around the margins of Antarctica in particular.
Even twilight images are proving useful with this LEAP project, but are they the same as using regular Landsat images? Are there any adjustments that have to be made in processing or in using these images?
So the twilight images defined in LEAP are really no different than any other Landsat image. It's just that imagery is collected when the sun is less than 5 degrees above the horizon, and this only occurs at polar latitudes when Landsat is passing over and imaging. No adjustments are really made to the data during processing, and these twilight images are just processed exactly like any other Landsat image.
How many extra images are part of this extended acquisition?
The LEAP special request process defines 306 individual WRS-2 path rows for Antarctica, Greenland, and Arctic sea ice regions.
The path row system is called WRS. That stands for
World Reference System 2.
Basically the grid of Landsat scenes that is used to identify which scene is which.
That's correct. So this roughly is equal to 21 images per day for each observatory. Further to this, Landsat 8 and Landsat 9 flight operations and mission planning have a prioritized scheme that they use to acquire data based on a proposed schedule that has been defined by the Landsat project scientist and data acquisition manager based on the requirements in the Landsat long-term acquisition plan, or what's referred to as LTAP.
So we're asking Landsat 8 and 9 to work overtime. Are they okay with that?
Well, Landsat 8 and Landsat 9, with their operational land imager and thermal infrared sensor instruments, are always on when they're flying. And so it's just a matter of whether they're actually recording the image data. When the Landsat 8 space and ground segments were being designed and developed, they were required to at least handle up to 500 images per day. That would be 450 descending daylit images and 50 ascending nighttime images based on our prior experience with the Landsat 7 image acquisition capability. However, during development, it was realized that Landsat 8 could acquire more images, so the USGS ground system was established with the ability to receive and process up to 740 images per day. So after launch, the USGS quickly found out that Landsat could image much more of the globe, and thus started the capability to incrementally expand imaging of the polar regions. Prior Landsat missions had imaged polar regions, but in a much more limited and episodic fashion, because at that time, observatory duty cycles, onboard recording, and downlinking were much more constrained. Landsat 9 was developed with all these lessons in mind, and while we can image the poles so systematically today. And so what LEAP does is it's just the next advancement that's come with Landsat 8 and Landsat 9 together. So to answer your question, Landsat 8 and Landsat 9 are not really working overtime, they're just acquiring more data because it's clear that the data is useful and beneficial to polar science. The number of images USGS acquires per day actually fluctuates based on the seasonal Earth-Sun geometry and is often below 750 images per day unless we're at the equinoxes where illumination is equally distributed across both poles. LEAP is well within our reach as we're learning, and the payoff for polar and climate science is expected to be tremendous once fully realized.
So the roughly 750 scenes per day, that's
an average, okay. And it fluctuates. It can go anywhere down to 660 all the way up to 850.
The sensors can manage that workload.
That's right, yeah. It's because we keep the recorder at a certain level of capacity. I believe each recorder on board is only, it's managed at 20%. And so when the data starts exceeding that, we're then finding ground contacts to downlink that data. Okay. And so because of the number of passes that we have now in our ground network, we're able to acquire, store, and downlink data in a fairly routine fashion. And so that's what enables now this capability. But it is important to highlight that the number of images fluctuates. And it fluctuates because of the criteria that we have in place to define acquisitions. And so, we've worked closely with flight operations and mission planning to basically see what we can do in terms of extended mode. So we vet all of these special requests ahead of time to be sure that we're not using the solid state recorder on board to utilization that would be somewhat create risk. And I could go on and on, but I'm not going to.
I know. What are some specific examples of how this extra data will help in studies?
Yeah, that's a great question. So we've already talked about how temperatures are warming and the polar regions are changing very rapidly. There are rare events such as ice shelf breakup or rapid movement of ice flows off glaciers that can happen even during the winter time. Or the polar twilight has been defined by LEAP, given the ongoing ocean and atmospheric temperature changes that's being observed. So with Landsat 8 and Landsat 9 now operating together in their global survey missions, their orbital treks converge at the poles, and this offers really near daily coverage because their image paths are overlapping as they descend or over the poles. So extending the ability to observe ice and polar ocean changes in the twilight just simply increases the probability of capturing these major calving events or even being able to see the preconditioning that's happening that will lead to a major rare event. And then we can also examine wind-driven surface melting, and then some of the open ocean ice shelf interactions that occur. And we're expecting sort of the warming to continue to lead to these kind of changes if it doesn't slow. So Landsat has been observing these polar changes systematically since 2013 when Landsat 8 was launched. And so the Twilight imaging is just starting to extend the record of observations to the full annual cycle, and we expect that this will unleash new science applications and then more routine climate monitoring of the polar regions, for example. Both TIR's thermal infrared sensors on Landsat 8 and Landsat 9 are exceptional thermal infrared imagers. What has been surprising actually to see with these early LEAP images is that there's pretty prominent spatial variability in surface temperatures near the ocean ice boundary. And also, as I've talked already, is these warm pools called polynyas, where that's upwelling water coming from deep in the ocean. And so the cold air pooling on the ice sheets are also possible with the TIRS instrument, and this has helped to identify some of the coldest places on Earth. For sea ice, if we image the ice dynamics in the winter twilight, we can more fully quantify the role of coastal sea ice formation and decay, or what's referred to as melange, which is a sort of a combination of ice blocks and sea ice and glacier fronts. And so the melange helps to stabilize the ice frontal zone, because that's what's holding back all the land ice that's wanting to flow into the ocean. And so another gap that could be addressed with this data is how winter ocean circulation is contributing to ice shelf stability, or what's referred to as basal ice melting. I think one of the most sensitive regions that's been identified is on the Antarctic Peninsula. This is the area of south of South America, and this is a region that's also really rapidly changing. There's several scientific studies that have already used Landsat 8 data to quantify the ice velocity and discharge, and it's showing that it's tipping the scales towards substantial quantities of glacial mass loss. And this is highlighting that this is likely a bellwether for future ice loss around Antarctica. And there's also, this is the region where we were able to observe, I think with Landsat 7, the infamous Larsen B ice shelf collapse that was located on this peninsula. And that was a major breakup event in 2002. And among that ice collapse of that ice shelf, there's continued to be smaller ice shelves that have continued to collapse since that time. So the key here is that Landsat's coverage in the past was much more sparse. It began to accelerate with Landsat 8's launch in 2013, and now with Landsat 9, we're now providing a routine monitoring of the Antarctic Peninsula, and the Twilight observations with LEAP simply extend the probability, again, of observing these major ice breakup events promoted by warming that are really known to occur on the Antarctic Peninsula.
Why didn't we think of this sooner? Why are we only doing these dark, high-latitude acquisitions in the last couple of years?
Yeah, that's a really great question. And I first want to start answering your question by recognizing that this work on LEAP is really led by Ted Scampos at the University of Colorado Boulder. He's has been a Landsat science team member for the past 10 years from 2012 to 2022. And Ted has been instrumental in helping the USGS advance their polar acquisition strategy from Landsat. And then working with Ted is Chris Schumann at NASA Goddard, who's a glaciologist, Mark Fonstock at University of Alaska Fairbanks, who's a glaciologist, and then Tasha Snow at the Colorado Schools of Mine, who's a geophysicist. And my role in this team is to sort of support their efforts and enable the data acquisition. And so what we did back in 2019 with Landsat 8 was to conduct a few Twilight imaging experiments that both had USGS and NASA participation. And what we learned from that experiment, and we did this over the Petermann Glacier in northern part of Greenland, that we learned that the operational land imager on Landsat 8 could return high-quality visible and infrared image data when the sun is less than 5 degrees on the horizon. And this is really possible because OLI has exceptional signal-to-noise performance in low illumination conditions and over surfaces that have low reflected radiance. And so what we learned is that, wow, it's really possible to learn more about the ice and the shadowing changes as well with the changes in the sun on the horizon, so we could actually see more at a lower sun angle. And then with the thermal infrared sensor, having that 100-meter spatial resolution really far exceeds anything that's been possible with instruments like MODIS that have 500-meter thermal observations. So I think to answer your question about not sooner, we just simply didn't have the capability to image in the twilight with Landsat instruments prior to Landsat 8. And it's taken us a while to understand how to optimize the use of Landsat 8 and Landsat 9, both individually and together as an observatory constellation for polar monitoring. And in fact, I still think we're still evaluating the capabilities for advancement specifically in the polar regions. And this is kind of how remote sensing science goes. It's incremental, steady progress based on technology evolution, prior knowledge, and implementation of lessons learned, as well as observing observational needs and applications.
Are other special requests ever brought to Landsat outside of that normal acquisition schedule?
Yes, you'd be surprised. The USGS is actually fielding several types of imaging special requests now that includes systematic monitoring of 100 active volcanoes. We're observing wildland forest fires at night across the western U.S. to resolve the active fire front. We're observing geothermal and urban heat island hotspots at night, and we're also tracking humanitarian migration at night. And LEAP is just one part of this special request capability that we have for Landsat 8, Landsat 9, and this is something that is, we're seeing an acceleration. And so what happens is that a user will go to the Landsat data acquisition page and they can submit a form online, and then that form gets submitted to what we refer to as the user portal. And that's when it starts to hit the data acquisition management, it starts to hit flight operations and mission planning. And we evaluate that request together. And then the data acquisition manager approves that request if it's consistent with the science mission and the requirements, and there's no perceived technical challenges that would create risk. So these requests are fully vetted in advance and don't get improved unless they're acceptable. I really applaud the development engineers who created the current user portal we have. It's very friendly, and as a data acquisition manager, when I see a request come in, I can read and vet the information very quickly. And then they've got a nice mapping system where I can go in and click on, and I can see exactly where the request is coming from in terms of the WRS path row, and I can quickly evaluate whether it's acceptable or not. So it's very user friendly. If a particular user is interested in the LEAP data that the USGS is acquiring, this data has been released as a USGS data release, and you can navigate and it will tell you the regions where the data are being acquired, and you can identify the path row or the glacier or the ice shelf or the sea ice region, and that information is available through the USGS to search. And then you just follow the data acquisition request process. If you see something that that is not already in the inventory, it's really it'll take some time to to explore. And then in the inventory, if you're looking at Earth Explorer, for example, you can simply go in and search for the sun elevation metadata field and find the LEAP data. And the LEAP data is going to be any data with a sun elevation below 5 degrees for those specific regions that have been released in the USGS LEAP publication.
Thank you, Chris, for joining us for this episode of Eyes on Earth, where we talked about the Landsat Extended Acquisition of the Poles project and how it will help researchers study changes in polar regions. And thank you, listeners. Check out our social media accounts to watch for our newest episodes. You can also subscribe to us on Apple and YouTube podcasts.
This podcast
This podcast
is product
is product of the U.S. Geological Survey, Department of Interior.